Okay, so my talk is going to be on nearly right. And Oblivious algorithms. For explainable clustering. Okay, and this is based on a joint work with Shinrich, Budimagamonov, and Rostanson. All four of us are at the moment in PAL, but Budima is defending this Friday, so it's not going to be the case for long. And yeah, this is going to be a clustering talk. So you all know some kind of clustering. You have a bunch of objects. You want to group similar objects together. But let's be a bit more precise about what we mean clustering in this sense. So the input will be a collection of endpoints, x1 to xn, living in R2D, and an integer k. And our goal is to partition the set X into k clusters. So we want to output C1 to Ck partition X. And we want to minimize some objective functions. There can be many. So my favorite one will be that. So we're going to minimize cost of this C1 to Ck, defined as the sum over clusters. For each cluster, a cluster is just a collection of points. For each cluster, we can think of a center, and we pick the best center. So it's a minimum over all possible points in R to the D. The center is not going, it's not necessarily going to be a point from the input. We sum over the points in this cluster over a distance from the point to a center, and in this case, we'll focus on just the L1 norm. And you can like this minimum, it's like here you can put any distance, but if it's an L1 norm, then this minimum turns out to be the median of the cluster, which means in each dimension separately you take the median. So you can rewrite it as just this part. You can rewrite as just sum over points, the distance from X in median of the cluster. And for that reason, this is often called K medians. There are other objectives. If you don't like L1 norm, you can consider L2 norm. So an alternative would be to put 2 here and take it squared. I have something to erase the board.
On the left of the
big one?
Yeah.
Okay. In the general definition, I can replace L1 norm with L2 norm squared, and then it turns out that a good center is just to take the mean point of the cluster, and this gives an objective called K means. And if you really like generalization, you can just put any p here, any p norm to the power of p. You'll get some p norm clustering, whatever. I'm not an expert in clustering. I guess there are some experts here. What is important is that you can find an approximate solution in a constant factor approximation. I think the best result for k-medians is in the 2-yard. Okay.
The K is not a constant for you.
P?
K.
K.
The number of clusters.
The number of clusters is not a constant. It's in there. Okay, so I told you what is clustering. I guess you already knew that. Now, what is explainable? So this is like a hot word right now in the AI ML community. The idea is that we have very complex models, they make some decisions, and we don't really understand where these decisions come from. So we'd like to have some way to understanding them, to explain them. For example, an algorithm decides that this person should go to jail, this one should be released, or an autonomous car decides to run into a track. We'd like to understand why. To have some explanation that we can make some sense of it. This is not anything this is not a strict mathematical definition. This is just some concept. You can define it in many ways. So how can we apply this concept to clustering? Let's think about k-means. The clustering is defined uniquely by centers. If you just pick some centers, then it always makes sense to assign a point to the closest center. So we have some centers, and since you assign each point to the closest center, then the way you assign points is based on the Voronoi diagram of these centers. So the picture looks like that. So what splits centers are hyperplanes, are some linear combinations of your features, of the coordinates of the points. So if a point ends up in this cluster, well, you can explain that it was larger than this hyperplane and larger than this hyperplane. So let's think of some real-world example. Let's say maybe this is some h and this is weight. And you say a person ends up in this cluster because 0.8 times h minus 0.2 times weight, at least 50, and 0.1 times h minus 0.9 times weight, or at least 70. Doesn't sound like a meaningful explanation. It would be much easier for us to interpret if we had something like h at least 20, weight at least 50. Let's say then you can donate blood or whatever. So this is bad. And this is nice. So coming from this example, we can think of a definition. This definition was given by Dasgupta et al. At ICML last year. So they defined a threshold tree. So in each node of the tree, you have a threshold cut, which is a dimension and a threshold. So let's say in the root you have x1 at least 20. This is either false or true. Let's say if it's false, okay, so this is our blue node. It gives this. Let's say if it's no, then this is cluster 1. And if it's yes, then we look at x2, compare it with x50. And this is our yellow cut. And C2 and so if the clustering is given by a threshold tree, we'll call it explainable. I gave you some intuitive motivation for this definition, but from now on, let's just take this and consider this as a math problem without going back to the original motivation. So now the natural question is, can we construct a clustering that is given by a threshold tree and it's still close to the optimum? So we would like to, but the tree induces some clustering. So as a shortcut, I can speak of a cost of a tree. And I want this cost compared to the cost of the optimum to be as small as possible. And what is the bound that we can get here?
Adam?
Yes.
Yes. So even if I give you the tree, I mean, I guess you still have to choose the center?
No, so there's no center. So the way I define clustering is just a partition of my points.
Because, wait, so this minimum over mu, what's going on there in the definition?
Yeah, so I evaluate the cost of the cluster is based on the best center for this cluster.
I see. So the best center is like automatically deduced from the clustering, and that's part of the definition.
Yes.
Okay. I see.
So if I want an optimal clustering, I can just give you centers. But this won't be explainable in that sense. If I want explainable, I give you a tree. This induces a partition, and then to compute the cost, you find center.
But when you say I give you a tree, you also give me coordinates where you range, or
yes. I give you this set of this whole tree, right? So this is each cut is a dimension and a threshold, like two numbers, right? Okay, and well, this value is they call it price of explainability. The optimal clustering, like without any constraints.
think about this thinking of what's the
Sorry?
Can you think about the thinking of for k-means or k-median? Or
So I can, so k-means, k-median, whatever else is my objective function. The way I evaluate the cluster. And I can apply this concept to each of these objective functions. So for a given objective function, I can think of how much worse are explainable clusterings than optimal clustering. And this will differ depending on the objective function. And in this talk, I will focus on k-medians because it has the nicest structure. These results generalize with different factors to other norms.
okay, so
Yeah.
do you have any bounds how complex your tree is? Like how many nodes you allow, etc.?
So I want to have k leaves because each leaf defines the cluster.
Okay.
So yeah, maybe I should start that. Because if I allow for a arbitrary number of leaves, I can basically put each point into a each cluster to be just an end of this kind of inequality.
Also, with every node of the tree, you request to partition or to separate at least one cluster from the other.
No, I mean, I don't need, no. So a good example would be, if I understood your question, the question was,
so you say that every.
So I can have here another branch, and here to have C1 and C4.
Yeah, but you're not allowed to. So in hyperplace, you doesn't separate anything. So if you consider stuff already stuff free.
Okay. So you asked me if I can add another cut here. Yep. I could, but it doesn't make sense. I think the answer is no. So in the end, I want to have k-leaves. And then the points, each point goes through this tree and ends up in one cluster. If one of my clusters is empty, then probably this is not the best solution. But I can have empty clusters. That doesn't. Okay. So this was explainable. So now some.
Excuse me, I want to understand because I understood differently Pedro's question.
Okay.
So can you have below x2 greater than 50? Can you have x2 less or equal than 20 or 10, something like that?
Yes, I can ask multiple times about this single.
Okay.
Yeah. Good. So now let's go to algorithms. Okay, so first I present to an algorithm that was given by those guys who defined the problem. So our first step will be to compute some clustering. And we can use for this constant factor approximation algorithm. So we have some clustering that is close to optimal, but it's not explainable. And we start from that. So our input to the main part of the algorithm is a collection of k-centers, mu1 to mu k. And of course the original inputs. And now what I want to do is so I have this center. Maybe this is right. Something like this. They define some clustering. Now I want to have a explainable clustering that approximates this well. So I will always compare to this initial clustering, and I won't assume that it's close to optimal or something. It just makes sense to use a good algorithm to generate it. So I will create some cuts to put each center of this, or its original center to a separate cluster. And okay, so in the first node of my tree, let's say I do this. Okay, this was not the last example. Okay, whatever. Okay, now in this node, okay, so let's say I had a point here. In the original clustering, it was assigned to this cluster to this center. Now it will end up in the other part of the tree, so it will have to be assigned to one of these centers. So I will pay some cost for it. And this process continues. So these are two clusters. And the algorithm that they propose, so what I didn't say is how to choose a cut. And what they propose is to choose a cut that minimizes the number of points that are misclassified, or the points that get separated from their center. Right, so they minimize the number of points that was that one. And what they show is that, okay, so let's write it. Cut number of separated points. This turns out to be O of k approximation for k medians, and O of k squared approximation for k medians. So this is the Dasgupta et al. Then there was a follow-up work with a more complex way of choosing cuts that works well if the dimension is small. It was something like d log k. And now we came up with a simple algorithm. We say, let's just take a random cut. Uniformly at random. Random cut. And we proved that this is log squared k approximation for k medians. Sorry?
Uniformly over what?
So we want every cut to be equally likely. So what we do is we take a bounding box of the centers. More colors. This is the bounding box of the centers. Now you choose dimension proportional to the length of the bounding box in this dimension, and then from this range to pick a uniformly random point. So this is one way of thinking about it. Other way of thinking about it is that let's say this is x1, this is x2. So I can draw a segment of length x1 plus x2. Have a part of length x1, have a part of length x2. I pick a random point in this segment. If it's this part, then this will be a cut in this dimension. If it's this part, it will be a cut in this dimension. Okay. So this is the algorithm. So we just generate these cuts until all the centers are separated. Which means we do not we do not look at the points. Of course, we need the points to compute this original clustering. But if you look only at this second part, or if you abstract the problem to given some clustering produce an explainable clustering, then we do not look at the points, which explains the oblivious part. Yeah.
What is the setting of given sensors we want to make? Your goal is to come up with a good threshold tree that is good for a particular median objective.
Yeah, that's true. And it turns out that a random cut, random threshold tree in that sense is good. Like for any set of points, a random threshold tree would be good in expectation. So I don't need to look at the points, I just need to look at the centers, which means that this is fast. Actually, Budima came up with a way to implement it in near linear time in the input size where you treat this as an input. And additional benefit is that it seems, if you think about, more of this machine learning part, this should generalize well. Since you do not depend on your input points, then whatever points come next, it should work for them. Though we were warned by people who know more about this stuff that this is not necessarily a good argument because the centers that we start with are based on the points. So there are some biases included in this point. So this argument is limited in scope.
Adam?
Yes.
How important is it, like in terms of the bounding box? Like if you picked a bigger bounding box that wasn't quite tight, would that make a difference?
If I pick a bigger bounding box, then some of the cuts that I draw would not separate any two centers.
Right. So it's sort of automatically, it doesn't matter, as long as the bounding box contains the centers, that's it?
Yeah, I mean, after I draw a cut, I need to check if it makes any progress, if it separates some points. If it doesn't, right, I cannot use it.
So I guess the conditional distribution on, whether you cut something would end up being the same as if you picked a tight bounding box. Is that kind of the idea?
Yes, that's correct.
Right. Okay.
You take a cut, you call it random, but then you check if the cut makes sense or not.
Yes.
And if it doesn't, you make the experiment again.
Yes, but I can make it so. Okay, I make the initial bounding box. The cut makes sense. The first cut, and now there are two ways of thinking about this algorithm. Either I draw the cuts from the same bounding box, and I look at all leaves of my current tree. And if any of these leaves is split by this cut, then I add this factor. Or I recompute the bounding boxes for both sides of the tree. And now in this side, I draw cuts from this bounding box. On this side, I draw cuts from this bounding box. This gives you the same distribution. It's just a different way of thinking about it. Okay.
So I'm still confused. Why is this motivator? The sense you have you know all the centers.
Yeah.
Then why are you clustering?
Because I want to have an explainable cluster. The centers define the cluster in a way that a point belongs to a closest center. Another question I ask is, if I want to have only these threshold cuts, can I still produce a clustering that is reasonable?
Are you assuming that the mu1 to mu are the precise the median centers?
So these are some centers. If I want to do it, like a reasonable choice is to run an approximation algorithm on your point, and this will give you some centers. I get the centers, they induce a clustering in the sense that each point is assigned to the closest center. This clustering is not explainable, and I want to make it explainable. Not losing too much. Okay, so I won't prove this log squared bound, but I can try to prove a slightly weaker bound that is theorem.
Could you try to replicate about
Yeah. So the random cut algorithm. This is the this one is log k times log C max over C min. I will explain it in a second. And C max is the largest distance between the centers and its centers. So this is like max over ij I max ej. And C min is just the minimum. Okay. So let me define one more thing. Let L denote the total size of the bounding box, the length of this segment. Nice. Okay, so the proof is in 3 easy steps. Step number 1. Expected cost of a single cut. This is at most C max divided by L times O. And there are 2 ways to see this.
Could you define what expected cost of a cut means?
What is the cost of a single cut?
Okay, what is the cost of a single cut? Sorry, I have this point. So a cut will separate some points from their centers, for example, this one. And I assume so this point will have to be assigned to some other center. So it will give us additional cost on top of the optimus. And I bound this cost by the C max. Because it is assigned to some other center. This is C max, this is the old cost, this is the new cost. So the increase in the cost is at most the maximum distance between the centers.
But that's the cost of its cut, depends on the previous cuts. Maybe you do the root, things cut several times.
You don't need this in analysis. In practice, it does. I mean, it gets lower, but for analysis, it doesn't matter. We can bound manage it. Okay, so okay, the cost of the cut depends on sorry, the cost of the actual cost of the cut is C max by L times opt. The probability that a point is cut, xi gets cut, separated from its center, you know, I have a point here. Say this is the closest center. So a bad cut is either here or here. So the probability of getting this cut is at most the distance, one distance from this point to this center. It is exactly the distance if the point is inside the bounding box, and at most if it's outside. So this probability is at most the distance from x to, let's denote mu of x as its center. And now when I sum this over all points.
Adam, do you have to divide by something?
Sorry?
Do you have to like divide by something somehow?
Yeah, that's right. Divided by L. Thanks.
And L is the total sum of the side lengths or just the maximum?
L is the total sum.
The total sum. Thank you.
So this is L. X1 is the length of this segment that I go from. Okay. So this I get. Okay. Now let me multiply both sides by Cmax. So now this is this, because it's the probability, the expected number of points cut times the cost we pay for each cut point. And here, this is the optimum, right? This is well, divided by L times Cmax. So this was step number 1. I think that should be enough for more for the other 2 steps. Okay, so step number 2 is showing that the probability that if I make log k times what I want to do, L divided by Cmax cuts half Cmax. This probability is high probability, 1 minus 1 over poly. Okay. So basically, I want to do log k times L divided by Cmax cuts, and I say that with good probability I can halve Cmax by that. So I want to separate all points that are at the maximum, all centers that are at the largest distance up to a factor of 2. Why is it true? Because each cut, okay, if the points are at the distance Cmax, well, between Cmax and Cmax divided by 2 from each other, the probability that I separate this point with a single cut is Cmax divided by L. If I multiply this, if I repeat this L over Cmax times, I get a constant probability of separating 2 points. So doing it O log k times, I get a polynomial probability, like polynomial Taylor probability, union bounding over k squared pairs of centers. I still get high probability. So this was like a quick way to convince you that this is true. And the expected cost of that many cuts is, well, you basically multiply this, the number of cuts, times the cost of the cut. These 2 things cancel. You got log k times opt. So you pay log k times opt to decrease your Cmax by 2. So you do it log Cmax by Cmin times, and you separate it all centers. Now, this same algorithm gets this bound. You just need to analyze in a slightly more complex way. And then there were 2 independent works. One appeared in ICML this year, the other will appear in Solar next year. And they both proved that this very same algorithm is actually of log k times log k. Okay. There are 2 open problems. One is, can we go down to log k? There is a lower bound, but we cannot be better than log k capacity. Like not in polynomial time, in general. I mean, there is a construction of the best explainable clustering is log k times worse than the best optimal clustering. This is one conditional. So the gap is really small, but based on like, we have an intuition that the right answer is basically 1 plus k minus first harmonic number. This seems like the tight answer, but we can prove it. They also couldn't so far. A second question, which is less well defined, is that since there is a big gap, right? I mean, this log k seems large. Can you come up with some clusterability assumption that makes your instance easy? Can you come up with some reasonable assumption that lets you say have constant price of explainability? And this seems hard because the log k lower bound that I mentioned, this is like a very clusterable instance. The centers are very far apart, all points are very close to them, but they are like on diagonals, so it's hard to count them with straight cuts. So we need a different notion if you want to. Okay, thanks a lot.